we go. Chain product and quotient rule, we're just going to kick it off today. I'm going to give you half of the chain rule, and I'm going to do the second half on Monday. So I'm not going to take you the full distance. I'm trying to break things up a little bit. There's the learning goals, success criteria, etc. Here is something, if you want to write this down, you can, but you don't have to. I don't really know why I wrote down the 3 deadly rules, but I want to really emphasise how important they are. This will make or break you. Ask anybody in Year 12, chain product quotient rule has been, for the last 3 terms for them, has been worth 20 to 30% of their exams. And it will come up in every exam from now on. Chain product and quotient rule. We touch on it again in Unit 3 next term and Unit 3 in Term 1. And I think we'll be doing some stuff to do with it in Term 2 next year. And probably also after your Unit 4 exam in Term 3, we'll be using the chain product and quotient rule. So please be aware of it, and please make sure that you walk out of class next Friday, approximately, next Wednesday with the chain rule, that you walk out and you know it and you're comfortable with it. We're going to be doing it for polynomials this term only. If you try and learn it properly next term, we're doing it for more complex functions. You've got other things to deal with. Okay? It's like the other thing you guys, a lot of you are doing now. You might be making the choice to learn how to drive an automatic car, and then you worry about the manual stuff later. You might not be, but some people do that, because then you've only got so many things to learn, and then you can learn the manual stuff once you're comfortable with this group of things. And it's the same here. We're doing an easy function. We're learning complex rules. If you get them down now, then it won't be an issue for you for the next year. So I'm desperate to get them right with you, okay? So there, I even wrote it in pink with a massive star, poorly drawn star, just to really emphasise it. And I underlined things in green, so it must be important. Rule number 1 is the chain rule, and I'm going to get you to do this question for me. We did an example quite similar to this last lesson, and I'm going to give you a hint. You can do this question without the chain rule, and it's obvious because obviously I haven't taught you the chain rule yet. So if you do know the chain rule, don't use the chain rule in this. On your tables now, talk about how you could do this question and do it, and then I'll do it with you. Okay, so 24, you're saying 24x squared plus 168. 168x, and you said 224. And Harvey says 294. Yeah. All right, let's do it. So without the chain rule, this question you're very capable of doing, and Dylan's just asked me about these rules. X plus a squared rule, x plus a cubed rule. You're welcome to go and memorise all those rules. There's a different one for x minus a squared and x minus a cubed. There's a different one for x plus a times x minus a. You can memorise all of them if you want. They're going to come up once or twice in your exam. I would encourage you just to know how to expand binomials and expand brackets, because then you don't have to memorise 100 million rules. 100 million might be an exaggeration, by the way. So you could expand this by recognising it's 2x plus 7 times 2x plus 7 times 2x plus 7. Now, let's ignore the third bracket and just do the first 2. So keep that in. You never do 3 brackets at once. It's the same as if I ask you right now to calculate 2 times 3 times 7, you will probably tell me, Harvey, it's...
What? No,
what's...
I'm saying in your answer, it's supposed to be 24x squared.
Oh, yeah, sorry. You 2 times 4, 3 times 7, you will work out and tell me it's 42. But I guarantee along the way, at some point in your mind, you thought of the number 6 or the number 21, because you did 2 times 3 first, and then you got that and multiplied by 7. You never multiply 3 things at once. You might feel like you do, but you never do. So we're not going to do that as well. We're just going to calculate this as 2x times 2x is 4x squared. 7 times 2x is 14x. 2x times 7 is 14x. 7 times 7 is 49. That times the last one, that's equal to 4x squared plus 28x plus 49 times 2x plus 7. Now we're going to do the next expansion. I'm going to do 2x. I'm going to do this by the distributive law, but I'm going to do it in one step. So the distributive law would be that everything in the first bracket has a 2x out the front of it, and plus everything in the first bracket times by 7. I'm going to do that now. I'm going to do everything times 2x first. Gives me 8x cubed plus 56x squared plus 98x. And then I'm going to do everything in the first bracket times 7. Gives me 28x squared plus 28 times 7, 30 times 7 is 210 minus 14, 196x, and 7 times 49 is 343. We will give you a couple of questions that are similar to this in your tech free exam, probably not quite to that extent, but you'll need to know how to multiply things that maybe give your answers up to 200. Be aware of that. And I have no problem if on the side of that answer you've done a long multiplication, whatever, get it right, that's the main thing. Anyway, 8x cubed, 56 plus 28 is 84, x squared, 98 plus 196 is 294x, and then plus 343, and therefore dy dx, using that rule, I get 3 comes out the front times 8x squared, because it lowers by 1, plus 2 comes out the front times 84x to the power of 1, because it lowers by 1, plus 294, and that gives me 24x squared plus 168x plus 294. Any questions? Now, just out of interest, before we go on to the next question, which I kind of want to hide from you, because I've got a Mr. Manson surprise for you, which usually for most people is not that exciting, but for me it is, and I don't care. Oh, it won't let me move stuff down. Just give me this. There we go. Okay, let's just do something very quickly. 24 divides by 2, 3, 4, 6, 8, 12, and 24. 168, I believe, is 7 times 24. Maybe somebody can tell me if I'm wrong. Sorry? Yeah, it is. It's 7 times 24. 294 is not divisible by 24. We're at 2 and 7. I think this is 3 times 8x squared. I think 3 is the best we can do. 3 into 168, what's that, 56? 3 into 294, what's that? 98. Oh, we can do better, can't we? Okay, I can take 6 out as a common factor. That makes that a 4. That makes that a 28, and that makes that a 49. There we go. So 6 out as a common factor. Now, interestingly, what I've got left in here is exactly the same as that. The process I'm following through now is to prove a point to you. It's not something you'd really need to do. But this, I could factorise that because I know it's this, and this thing was that thing squared. So actually, this is equal to 6 times 2x plus 7 squared. Okay, and just as a reminder, this process here is tricky, plus not really required. So I'm doing some factorising now. I know the answer, and I'm going there, but I'm trying to prove something to you. The interesting thing here is, though, zoom out a little bit, that if I derive this function, I get, this is 2x plus 7 cubed, I end up with 2x plus 7 squared. And that's what we get with polynomial differentiation, don't we? Except, see this 3, it's come out the front, but it's not 3 out the front, it's 6. So if you were asked to derive this, another thing you might do when you derive this is you might bring the 3 out the front and make it a 2. And you would almost have the right answer, but not quite. So it is that process. There is something else in play, which I'm going to show you now. But I want you to see there's a link. There is a clear link. Any questions on that? What is this? Oh, that's right. That's the guesses. Okay. Let's do this question. Y equals 2x plus 7 to the power of 30. Go. How long do you need?
Would it be 60 outside of 2x plus 7
To the 20. 60. What if I said to you, right now you have to tell me if you're willing to submit that answer. If it's right, I'll give you $100. If it's wrong, you've got to give me $100. Would you do it? You wouldn't do it. So you're less than 50% sure?
No,
or you're less than 99% sure and you're just not willing to lose $100. Okay, cool. See, money always gives me an honest answer. The point here is, I just wanted to see how sure you were. You followed the pattern from the previous question. You're just not convinced by the factor of 2, I'm assuming. Does the 30 go to 60 like the 3 went to 6 earlier? Are you convinced that's definitely a power of 29? Yeah? Okay, I'll tell you it definitely is a power of 29. Put your hand up if you think that is a 60 out the front or if there's a different rule in play. Hand up if you think it's 60. Hand up if you think it's something else. Okay, cool. Would you like me to just break the silence and tell you what it is? The answer is exactly that. Okay, now would you like me to tell you where the 2 comes from before I show you the process? It is, the 2 comes from that 2. If that was a 3, it would be 90 at the front. Here's the process. And then I'm going to stop. So this is the chain rule, and this is the moment. This is it. This is the moment where you collect all your focus, you follow what's going on. This is make or break the next year. Get the chain rule, get it sorted. I will teach it again and again and again, and I will try my best to make sure you're all on board. But for some of you, that might be till next term, so get it right now so that's not next term, okay? Instead, we use the chain rule. We don't want to expand a power 30. Even expanding the cube was a bit of a pain, let's be honest. We don't want to do a power 30, definitely don't want to do a power 30. So we're going to use the chain rule by introducing a new variable u. It could be called anything, but use the standard. You go into your textbook, it'll be u. You go into another resource, it'll be u. You go on a website, it'll be u. If they quote something in your external exam, it will probably be a u. The only time it's not really a u is if u's already been used in a question, and that's an a. Or maybe a v. I don't know. So the point is here, though, you could call it a smiley face. You could call it a tree. You could call it whatever you like. Use the standard. So we're going to say, let's introduce a new variable u, which is a function of x. And so we get this break up here, and that is that y was equal to f of x, but now y is going to be a function of u, which will be a lot simpler and differentiable. And u is a function of x. We've taken something out to simplify this expression. Okay? And this is the complex bit. But I'm going to do it through example. So I'm going to leave that bit up there, do it through example. Let's consider y equals 2x plus 7 to the power of 30. This is too complex for me because it's a function inside of another function. It's got 2x plus 7. So that 2x plus 7 in the previous work would have just been x. X to the power of 30 we can derive. But it's 2x plus 7, it's not x. So it's a function inside of another function. It's 2x plus 7 inside of the power of 30 function. So what I'm going to do is I'm going to swap 2x plus 7 for u, because that's differentiable. So I'm going to say let u equal 2x plus 7, and therefore y equals u to the power of 30. And then I can say that dy du is equal to 30 u to the power of 29. Okay, I'm now deriving y, not with respect to x, I'm deriving y with respect to u, dy to u. And so I do the rule's exactly the same. Bring the power down, decrease the power by 1, just I'm using the u. But now I've got dy to u, I want dy dx, don't I? And this is where I use the chain rule. Over here, this is, when I reference the chain rule, this is what I'm talking about. This is a fractional argument. It doesn't quite work like fractions, but it does work in this case. Dy dx, the thing we want to find, is equal to dy to u times du dx, because the du's cancel out, leaving us dy dx. Can we see that kind of fractional argument there? So I already know dy to u, don't I? I just need to find du dx. So over here to the side, I say, well, u is equal to 2x plus 7, and therefore du dx is just equal to 2. Because when I derive 2x plus 7, the 7 becomes 0, the 2x becomes 2. There's your factor of 2, and that's why it comes out like that. Okay? And then I use the chain rule, and I say, and dy dx, the thing I'm trying to find, is equal to dy du times du dx. You know how mathematicians are lazy? We're so lazy that I'm probably going to start using dots sometimes instead of multiply. Okay? And then I'll be saving virtual ink, which is pretty good. So it might happen, and it happens in a chain rule a lot. Anyway, dy du is equal to 30 u to the power of 29, and du dx is equal to 2. I've got this from here, and I've got this from here. So that's just a straight substitution, and this is equal to 60 u to the power of 29. But I've got dy dx in terms of u. I don't want dy dx in terms of u, so I'll always have to do one last thing, and that is take u out, substitute what it's equal to in, and so I get 60 2x plus 7 to the power of 29. Just swap the u for what it's equal to. That's the chain rule. And that's pretty much what I'm going to show you today, except maybe a couple of examples. But it is that simple, and actually there's an observation way which doesn't involve this level of working, which I'll show you on Monday, but I'm going to go on another one of those rants, because I teach the observation, because if I don't teach it, you will go and find it somewhere, and then you'll come back and tell me I didn't teach it to you. So I will teach it, but then people use the observation method in exams and get it wrong, because it's not as procedural, and then I cry. So we're not going to do that in that part, okay? That's the plan. I'll talk about that on Monday. But for now, I'm going to give you a couple of examples like this. I'm going to remind you how important this is. And then I'm going to talk about one other thing, which is the importance of some notation. What have I got here? I'm going to do 3 examples. So let's do them, and let's do them quickly. This is how I set it out. This is how I love setting it out, and I'm going to continue to do it like this. Without fail, half of my classes usually go and find another way to set it out, and that's fine. You set it out however you like. I like doing it like this. I'm going to start by saying let y equal u to the power of 7 and u equals x squared plus 2. So I always set it out side by side. And I've got my u substitution and my y is in terms of u. dy dx is equal to 7u to the power of 6. du dx, that's my apology, dy du. And then over here is du dx is equal to 2x plus 0, so just 2x. And therefore, dy dx is equal to dy du times du dx. Poor planning on my part in space. Just give myself a couple extra lines, which has also failed me. And it's failed me again. There we go. Oh, man. Let's try one more time, and then I'll just give up and throw the computer. There we go. We're good. Okay, so that's equal to dy du, which is 7u to the power of 6 times 2x, which is du dx, and that's 14 times x squared plus 2 to the power of 6. Now, if you do a few of these questions, you might spot the shortcut, and that's fine. If you spot the shortcut, that's fine. I'll teach it to you on Monday. B, so that's a standard example. You've seen 2 standard examples now. B is a little bit different. B can be done using something we'll learn later called the quotient rule, but it's actually easier with the chain rule, because I'm going to write this down as f of x is equal to x cubed plus 2x to the power of negative 1. That makes it a little bit easier. And I'm actually going to change f of x to y, because f of x is, notation-wise, it's a really challenging notation to get it to work well with the chain rule. So you get f of u and you can do stuff, but it's not as nice. So I'm going to go with y, and I'm going to say, because y and f are actually interchangeable, so I'm going to say y is equal to u to the power of negative 1, and u is equal to x cubed plus 2x, and then dy dx, so dy du, is equal to negative 1 u to the power of negative 2, and du dx is equal to 3x squared plus 2, and then therefore dy dx is equal to dy du times du dx, which is equal to negative 1 u to the negative 2 times by 3x squared plus 2, and I'm going to almost run out of space, but it's negative. The negative 1 just makes it negative. On top I get 3x squared plus 2, and on the bottom I get u squared, because it was u to the negative 2, so I'll flip it back to the bottom, and that is x cubed plus 2x squared. Now I do want to give you a little bit of time, so I might leave example 2, and I'll just leave it up on the board. You can have a go at it if you want. I'll do it on Monday first thing. I've got two things to say. Firstly, you have learnt there's a variety of notations. You can use dy dx, or you can use y dash, or you can use f dash of x, and there are other notations. X dot is another notation, there's a few others. In chain rule, and this is the only time this is going to happen in the methods course, dy dx is the best notation by a long way, because you can derive functions, Connor, with respect to different variables. So if you go and do maths at uni, you'll learn that you could have a function y equals xw, and you can derive that with respect to x or with respect to w, and it means different things. You're looking at the rate of change as w changes or the rate of change as x changes. You don't have to worry about that in the methods course. When we get to here though, if I just say y dash, I don't know whether I derive that with respect to u or with respect to x. So if you want to get your notation right, if you get a question that has u's and x's, you really should be using dy dx and dy du so that I know which one you're talking about. Otherwise, technically, your communication's not right. But you will, and the textbook should get that right, but you will see examples. There are resources out there where that notation might not be right, and technically it's not. So you've got to be a little bit careful with the notation. The second thing I'm going to say before I leave you is this is starting to get abstract. This is around about the point where people start to just make it very procedural and they forget what they're actually doing this for. So I usually hear around about now people going, oh yeah, I can do this, but I don't know why I'm doing it. So I'm going to keep on reminding you. Don't forget that when we differentiate, it gives us the gradient function. The gradient function tells us the gradient at any point on a curve. And that is really, really useful because we use curves and models to actually model data. And if we know the rate of change now, we can use the rate of change now to predict things in the future, which is pretty much the main premise for modelling data. So you might be modelling the financial markets to see what you think might happen. You might be modelling the speed of something to see what might happen there. You might be modelling something in a science experiment to predict what's going to happen to be able to change the conditions of the experiment. And rates of change help you to make those predictions. That's why you're doing it. Don't ever forget why you're doing it. There is a context, but we get pretty heavy into the algebra and the abstract. Excellent. Thanks for your listening. You've got 15 minutes. I want you to walk out of this classroom having done 5 questions and knowing how to use the chain rule. So if you're behind in your work, please, please, please still go on and do exercise 20C. I'll look that up. In fact, I'm going to go up here. 20B. No, 20B. Thanks.